everybody. This is the second part of the chapter 9, which is about design factors in orthodontic appliances. And before we proceed, some of the audience has told me that there was a problem with the sound in some slides of the first chapter, so I'm going to go over them again, which were mainly about the stress strain curve and some definitions in that and the different types of wire that are used in orthodontics. Strength is measured in units of stress, which is megapascal, and 1 megapascal equal to, let me show you here, 10.197 gram per centimeter, square centimeter. So Pascal means force or gram per centimeter, per the surface area. And the most commonly nowadays, the two units that are used, megapascal in orthodontics and gram per centimeter, square centimeter. Stiffness is proportional, as you can see here, to the slope of the elastic portion of the force. And it's opposite or reversely proportional to springiness. So springiness opposite to stiffness. So any stiffer wire will be less springy, and springier wire will be less stiff wire, less stiffer. So and you can see, since it represents the slope, the more vertical the slope is, the stiffer the wire is. The more horizontal the slope is, the more flexible the wire or springier. Range is defined as the distance that the wire will bend elastically before permanent deformation. This is the range. So the wire that can bend for long distance without having any permanent deformation means that it has high range. The wire that bend immediately after some bend permanently, this has a short or low range. On the other hand, spring back, if the wire bend permanently, its usefulness and its work in clinically represents the spring back. So the spring back represents the distance along the horizontal axis after deformation, after permanent deformation, beyond, when the wire bend beyond permanent formation. So it's a very important feature for which indicates the clinical performance of the wire. These three properties, strength, stiffness, and range, are very important when we evaluate wire properties on wire performance. Strength equal to stiffness times range. Two other important characteristics, resilience and formability. On the stress strain curve, the resilience, the area under stress strain curve out to the proportional limit. It represents the energy storage capacity of the wire, which is a combination of strength and springiness. So the wire that is more resilient means that it has more energy for the wire. Formability is the amount of permanent deformation that a wire can withstand before failing. So it's in the plastic limit. This one represents the elastic limit, and this is the plastic limit. So the wire is formable, so it can withstand a lot of bendings to create, for example, loops like the stainless steel, more formable than, for example, the Nitai or the Team A. The Team A less formable. So it's the amount of permanent deformation that a wire can withstand before failing, and it represents amount of permanent bending the wire will tolerate. And formable wire, opposite to it is formable versus fragile, that is easy to break. If we want to have an ideal arch wire, we need a wire that has high strength, low stiffness, high range, and high formability. You need strong wire, but not very stiff. So you can insert it. You can allow some activity for longer period of time, high range, and high formability. In addition, before we needed the wire to be weldable or solderable, so sometimes we can solder or weld a hook to it. Nowadays we don't need this feature because we have the crimpable hooks and other accessories. Another important point that was mentioned in the book, that how to measure dimensions. We usually measure dimension in inch or millimeter. The most commonly used unit is the inch. Like when we say 16 by 22 wire means 0.016 of the inch by 0.022 of the inch. And to make it shorter, they added this unit, which is mil. So instead of you saying 0.016 inch, you could say 16 mil. Instead of saying 16 mil by 16 by 22 mil. And in mil is not millimeter. Mil means 0.000 of the inch. While when we say millimeter, of course we convert the inch into millimeter. So 16 mil means 0.4 millimeter, and so forth. Mainly we use the inch instead of the mil, but there are some, especially the straight wires, you can see that they are, if you see a straight wire, you can see it's written on them sometimes 0.7 or 0.8 millimeter. Wires, or the material that were used to fabricate wires. At the beginning, gold was the best wire because it was intraorally tolerable and it's soft wire, but it needed a large diameter one to be used intraorally, to be used with brackets to deliver force because it was too soft. And then we had the precious metal alloys like the platinum and palladium, along with gold and copper, were useful for all dental purposes. And then with time we had the stainless steel wire, and which was introduced and made the metal alloys obsolete, no more used because they were precious and expensive. So now mainly they are used only to fabricate fixed lingual appliances like the retainers and fixed lingual stainless steel. With the introduction of stainless steel and cobalt chromium alloys, it was a breakthrough in orthodontics. The cobalt chromium and stainless steel are similar, except that cobalt chromium comes softer at the beginning, and it hardens with heat. So when you heat treat it, it will be hard like stainless steel. Stainless steel rust resistance, it resists rust nicely and tolerate intraoral environment. It comes from the high chromium content, and usually when we say the composition of the stainless steel wires consists of 18% chromium and 8% nickel, and this is the name where the name comes from, 18-8 stainless steel wire. So the stainless steel and cobalt chromiums are known to respond and change to heat treatment. So they can be hardened by cold working. So if you do a lot of bending in the wire, you can release these stresses, because when you bend the wire, you create stresses in the wire. So when you after you finish bending loops in the wire, and to redistribute the molecules in the areas of bending, you heat treat the wire, for example, are 70 or 60 or 50 Fahrenheit, 50 degrees centigrade, and this is what they call cold working. But if you try to heat it up to the melting point, then you expect the wire to be soft, so you soften the wire. It's called annealing, that when you heat treat the wire up to the red point or the melting point, then the wire turns to a soft or deadly soft wire, dead soft wire. So for example, for dead soft wire is steel ligature wire that we use. They are dead soft, and they are made soft so we can use them to tie wires on the brackets. Of course, there are some wires from these categories, they are called super grade wire, are almost brittle and very strong, very stiff wires, and break easily if bent sharply. So these super grades sometimes are used to flatten curved P, for example, like the Australian wires. The regular grade of orthodontic wires can be bent, and which is very good, has high spring back, can be bent to any desirable shape without breaking, so it's formable. Unlike the Team A, although we can bend it, but it's brittle, it might break easily. That's why the Team A wire, which is the beta titanium or titanium molybdenum alloy wire, comes ready-made with the T-loop. If you want T-loop wire, it comes ready-made and you can use it clinically according to the size you use. LG alloy, the cobalt chromium is called LG alloy, has the advantage that can be supplied, as I said, in softer form and therefore more formable state. So you can form or bend the wire the way you want, and then the wire can be hardened by heat treatment after being shaped. So the heat treatment increase strength significantly of the wire and make it similar to equivalent to stainless steel wire. Nowadays, unfortunately, this material disappeared from the market, and I don't see it that often except those straight wire that we use for wire bending exercise. Third and the most important wire is the nickel titanium wire, which we call night eye. Everybody is familiar with night eye, that we use to align and level teeth in the initial stages of orthodontic or fixed orthodontic appliance treatment. And why it's important? Because it has exceptional ability to deliver light force over longer period of time. And before having this night eye wire, as you know, the initial aligning or leveling was done with stainless steel wire that we add to it a lot of loops in between the brackets to increase the inter bracket distance, so increase its flexibility to make it easy to fit on the brackets that are greatly displaced in order to and at the same time keep its flexibility. So now with the introduction of nickel titanium wires, at that time it was really a big breakthrough in orthodontics, because it's very easy, made our life easier just to fit one night eye wire that has the ability to go back to its original shape and flexible without the need of those loops in the wire. And it's usually referred to as night eye with capital, 2 capital, N capital and T capital, and as is stated in this book. And also you can see that sometimes they call nitinol, like this one, and it comes in several trade names like orthanol, nitinol, this one night eye. So you expect to see a lot of names. And just before we proceed, the night eye wire is a family of wires, started with the regular night eye, which was called M night eye, and then we had the A night eye, which is super elastic wire, and finally we had we had heat activated wires. We call them hands. Sometimes they used to call them hands. And also we have nowadays the copper night eye wires also that were introduced lately, and they have copper in their components, which increased the conductivity of the wires, made it more conductive wire. And it has a reason for that. We'll talk about it later. In this part of the chapter 9, we're going to talk about force and its related terms or items that we use during fixed orthodontic appliance. And as you know, one of the problems of the fixed orthodontic appliance is that we apply the force on the crown away from what we call the center of resistance that comes in the middle of the root. And you know from your general knowledge that when you apply a force away from center of resistance, which is equivalent to center of mass in free body, you expect the teeth to tip or that body to move or to rotate. So in orthodontics, because the tooth is engaged in bone, we expect it to tip. So our task is to use the force to do with the fixed appliance not only to do tipping. No, we want to achieve bodily movement sometimes, and we want to do root movement, and we have to know how to control the force. What is force? Force is a load applied to an object that will tend to move it to a different position in space. And usually it's measured in newtons, and in clinically we use the units of grams or ounces. And for your information, 1 Newton is equal to almost more or less equal to 100 grams of force. What is center of resistance? As I said, it's a point at which resistance to movement can be concentrated for mathematical analysis. So free object in space, we call it the center of mass. Center of resistance occurs at the center of mass. But with this object, the tooth, which is partially restrained in bone, so expect the center of resistance will be in the middle of the crown when we call it center of resistance. And it's approximately midpoint of the embedded portion of the root. So if we have the embedded portion shorter, like in cases with periodontal and bone loss, so we expect the center of resistance to move more apically. So as I told you, this is our problem. So when we apply force, we apply it at the level of the crown. That's why we apply it at the distance from the center of resistance, and that's why we expect to have tipping movement. Moment, it's a tendency to rotate an object around some point. And why it occurs? It occurs when we apply the force away from its center of resistance, and it's equal to the force applied times the distance from the center of resistance. So we say moment of 50 gram millimeters, and this is our problem. So when we apply the force, we always expect to have moment of the force, we call it MF, moment of the force, that usually tends to tip the teeth. So let's consider this MF as our enemy that we try to resist in order to avoid tipping, and apply counteracting moment in a way or another to resist tipping and allow only net movement of the tooth bodily. Couple, definition of the couple: two equal forces, equal in magnitude and opposite in direction, but not on the same line, non-collinear forces. So these two forces, if applied on an object, they tend to rotate the tooth around its center of resistance. So the tooth will not move. The movement will be constant, just rotation, spinning the object around its center of resistance. But as I said, there are two forces equal in magnitude and opposite in direction. So when we use fixed apply, let's imagine how we can control tooth movement and prevent tipping. The author here is given a very nice example in this figure. So we can apply, for example, if we apply 50 grams of force in the lingual direction, let me just open the laser pointer here so you can follow me. If we apply 50 grams in the lingual direction, we expect the tooth to tip because it's away from center of resistance by 15 millimeters. And how much this moment that will be created, which we call MF, is around 750 grams of force. 750 grams of force. And in order to prevent this tipping and allow bodily movement, we can apply a lingual force that is directed labially. So when we talk about force, we have to talk about the force and add to it the unit, gram, and the direction of the force. We say 50 gram in the lingual direction, or 37.5 gram in the labial direction. So the author is suggesting 37.5 gram in the labial direction from the lingual. And why is that? It will be adequate to prevent tipping. So this force will create a moment that is, the force of application point is 20 millimeter away from center of resistance. So when you look at the moment when you measure the moment that is created by this 37.5 gram in the labial direction, it will be equal to, again, 750 gram millimeter. However, because this force is smaller than 50 gram, which was closer to the center of resistance, the net movement will be around 12, the difference between the two, 12.5 gram of force in the lingual direction, and this will prevent tipping. So the net results will be a lingually positioned or directed force, which is 12.5, plus couple the moment of the force, MF, and another moment of the couple or counteracting moment, that because they are equal, we will cancel any tendency for rotation. We expect the tooth to move lingually in lingual direction. But because the force here is very small amount, 12.5 gram, is not adequate to move the teeth, so the author is suggesting that we can apply more force, like 200 gram here and 150 grams. So this will allow the teeth to move in a lingual direction with adequate net 50 gram of force. And what in orthodontic appliance, we don't do this. We apply also couple inside the bracket, which is applied or exerted by the edges of the wire, because when we use rectangular wire in rectangular slot bracket, which has, the wire should have adequate diameter, then when we apply lingual force, we expect the tooth to start tipping because it's away from center of resistance. But because the two edges will start to touch the bracket inside the brackets, the minute the bracket tend to tip back, then we expect to generate a couple inside that is equal 50 gram force on each side. This is the couple force, the couple of the force. This will generate a moment that is opposite in direction, that will be adequate to prevent or resist the tipping. How can we measure couple? Couple is measured by measuring one of the forces times the distance between them. So you say if this distance is 5 millimeter, then you say 50 times 5, then it will be equal to 250 again gram millimeter, and we call this the moment equivalent. So when we measure the couple, we use moment equivalent, and usually it's our weapon that we use to resist moment of the force when we use fixed orthodontic appliance. Another important definition is center of rotation, the point around which rotation occurs. So for example, if the tooth will rotate in a pure way, pure rotation way, we expect it to rotate around center of resistance. So the center of rotation will be at the center of resistance, which is difficult to achieve. We don't have pure rotation. We don't expect the tooth to rotate purely because it's contained in the bone. And there are other examples we're going to talk about. We know how to control forces, their moments, and how to use couples to overcome moments, then we can achieve the type of tooth movement that we want, whether it's tipping or bodily movement or root movement. These are three important movements: tipping, bodily movement, and root movement, in addition to intrusion and extrusion. Let's take this example, the one that is mentioned in the book. For example, if you want just to tip proclined incisor lingually, so by removable appliance with a labial bow, active labial bow, you can apply lingually directed force, and this will create a moment that will tip the crown lingually, but at the same time it might move the root apex a little bit labially, which we call uncontrolled tipping, but sometimes it's desirable. If you want to do a bodily movement, perfect bodily movement, then we have to apply, before we go to that, doing this kind of tipping can also be achieved by our fixed appliance if we can, like if we fit round wire and try to retract incisors on round wire. So what do you expect? You expect the tooth to tip lingually. Why? Because the wire is touching the bracket, inside the bracket, on only one point contact. So expect the tooth to tip lingually. If you want to do bodily movement, then we have to apply this model. Lingual opposite, in addition to the labial force, which is lingually direct, we need another lingual force opposite in direction towards the labial. And for example, if this force is going to be 200 grams, this will be 150 grams. And this is how we control our movement. If we want to have more root movement instead of crown movement, then we have to increase the counteracting moment to make it larger than the moment of the force. This is how we control our tooth movement. So how we can overcome this moment? Just to remind you again that the force, because it's at the crown, it will create moment, which we call MF, which is the bad guy. What we want to do, we want to achieve or apply opposite moment, which we call counteracting moment. And we have like 2 or 3 ways of doing it. And there's another way to decrease the magnitude of the moment, is to apply the force at the center of resistance. If we apply the force at the center of resistance, then we expect the tooth to move bodily, which is impossible and difficult because we don't have access to center of resistance. But for appliance, we can do something similar to bring the center of resistance or the force application closer to center of resistance. Let's say center of resistance here for the canine. So we apply hook, and then the line of action of the force should be at the level of the hook, not here. So when you apply the force here, you are applying the force closer to center of resistance, which means that you're going to minimize the moment of the force. It's a way to do it, but it's not a perfect solution because it will not prevent, it will minimize the moment created. Because also it's difficult to apply a very long hook that goes up to center of resistance because it's going to be flexible, it might break, and also it's it interferes with oral hygiene. Same thing applies to the lower. But this also, you can use this during the fixed appliance with twin block that will resist the tipping effect. And you know, with our fixed appliance, this is what we call twin brackets. When we have the twin brackets here, the twin brackets itself inside, it applies what we call the 2-point contact. So it will resist tipping the minute, let's say we're trying to retract the canine backward in the distal direction. So if you try to move the tooth in distal direction, the tooth, because the force at the level of the crown, it's away from center of resistance, we expect the tooth to tip. What resists this tipping is the 2-point inside the bracket. So the minute the bracket tends to tip over the wire will generate the couple inside that will resist the moment of the force by creating an opposite moment, which we call moment of the couple. Although we apply this principle when we retract canine, but sometimes due to many other reasons, like for example, when we use softer wire than it should be, we expect the canine to tip backward, or sometimes the wire bend by itself, and sometimes the wire comes out of the bracket. We don't use enough ligation around the canine that we expect the tooth to tip. That's why sometimes we need to apply these types of mechanics, applying long crimpable hook to distalize the tooth lingually. And nowadays, with the application of the mini screws, if we want to achieve more bodily movement, we can put mini screws opposite مثلا mesial to the first molar, and then we hook power chain or coil spring to the we call it power arms. So this will minimize the tipping expected during tooth movement. This is a way of doing it. So the other way of doing, applying, as I said, another force that will create a moment, as we showed in our previous example, and this can be achieved either by the old way, which is by using big concepts that he used a lot of auxiliary wires, like for example here, this is a torquing spring, or these are torquing springs. So when they are fabricated outside, they are in horizontal direction. So when you fit the wire, force it in, they will go labial, go upward, and then they will be activated by applying lingual force. So we have lingually directed force here in the bracket, inside the bracket. At the same time, we have another point that is touching the crown more gingivally, and this will create opposite force to torque the root lingually. So this is also another example of two-point contact. One point inside the bracket and another point at the level of the spring. So applying these two-point contact will create a couple that will counteract the moment of the force that we don't like. Practical way of applying two-point contact is by using rectangular wire, as explained here. Rectangular wire when we apply lingually positioned force. So when we use round wire, the round wire will touch the bracket in one-point contact. So expect any lingual force will tip the teeth because the moment of the force will prevail. There's nothing to prevent it. So it will tip lingually. But if we apply rectangular wire inside, so the rectangular wire, the minute the tooth start to tip lingually, a couple that will be generated inside the bracket that will resist the movement, the tipping this way. So the couple, when it's generated, it will create moment equivalent, or the moment of the force, the moment of the couple, or we call it counteracting moment, that will try to resist the tipping by applying lingual moment, counteracting moment, which is in counterclockwise direction, and then we expect to have bodily movement. And by doing so, we can control our movement. If we want to do just by round wire, we can do tipping. By rectangular wire, we can do bodily movement. If we want to do more like root movement, then we have to create additional torque or twisting of the wire inside the bracket to generate a larger counteracting moment, and by doing so we expect the tooth or the root to tip lingually. So we have to control or try to balance between the moment of the force and the counteracting moment in order to reach the objective that we want to achieve. And this is the example that was described earlier. So if we want to create couple instead of applying these two forces, and we want to create a couple inside the bracket, then we have to have torsional force by calculating a torsional force of 1,500 grams, which will be adequate to create a couple which is 50 grams on each side. That will create an adequate moment or counteracting moment to allow bodily movement to occur. So one of the disadvantages of this technique is when we apply couple inside the bracket, the force, because the two forces are at a very small distance. Usually, how do you measure the couple? As I said before, moment, or the couple will be one of the forces times the distance between them. So here the distance between the two forces is very minimal, 0.5 millimeter or smaller. Then we expect the movement will be limited unless we use a very large forces inside the bracket, which is sometimes problematic. We cannot do that. And the easier way, or the more practical from this point of view, is to apply 2-point contact, one in the bracket, one away, like those torquing or auxiliary springs that are used in big appliances. So as I said earlier, to control our movement and to control a root position, we need to balance between the moment of the force, which is the bad guy, and the counteracting moment. So if we have the counteracting, if we apply counteracting equal to the moment of the force, then we expect to have bodily movement, right? If we have the counteracting 0, if the ratio of the counteracting over the moment of the force is 0, which means the counteracting is 0, then we expect to have pure tipping or rotation around center of resistance. If the counteracting moment is smaller than moment of the force, in other words, the counteracting moments over the moment of the force is somewhere between 0 and 1, then we still have tipping, but it's controlled. Controlled tipping means that the tooth will tip around its root, apex. If we have the opposite, that the counteracting moment over the moment of the force, the ratio is more than 1, then we expect to have torque or root movement. So this is how we control our movement. Balancing these two moments. Moment of the force versus moment, the counteracting moment or the moment of the couple. So here, if the moment of the couple or counteracting over the moment of the force is 0, this means the counteracting is 0, then we don't have any counteracting, then we expect the tooth to move by rotation. And this is if we want to have control tipping. So expect control tipping means that we allow the tooth to move and rotate around its apex. And then if we want to do bodily movement, moment of the couple over the moment of the force equal to 1, we expect the center of rotation to be at infinity. There is no center of rotation because there is no bodily movement. And if we have the opposite, the counteracting moment larger than the moment of the force, the ratio is more than 1, then we expect to have more root movement than crown movement, which makes the center of rotation at the apex or somewhere around somewhere on the line between center of resistance and the incisor edge. So there is another way to measure or compare, or to measure, sorry, and balance between the moment of the force and the counteracting moment by the moment to force ratio. The moment to force ratio is a term that was used previously by biomechanics people to, in a way that they wanted to calculate the moment and the force to design an appliance that exactly can move teeth bodily. So they were trying to do bodily movement, and they thought that they want to generate moment to force ratio of 8 to 10 in order to produce bodily movement. Why 8 to 10? Depending on the length of the root. So they want, what do we mean by moment to force ratio? The counteracting moment ratio to the force applied should be 8 to 10, somewhere between 8 to 10. And when we apply it this way, this will create bodily movement. If the counteracting moment ratio to the force is less than 8 to 10, between 1 to 7, then we expect to have tipping movement. If the counteracting moment to the force ratio is more than 8 to 10, then we expect the tooth to have more root movement than bodily movement. So this is another term that you're going to read somewhere, which is moment to force ratio. Another important point to understand that we should not underestimate what we call friction, because when we apply force, the part of the force will be dissipated to overcome friction, and the force felt by the tooth is less than the force applied, while the couple that we create within the bracket is much larger. It's supposed to be not much larger, it's supposed to be larger than, or the moment created by the force of the forces of the couple inside the brackets is expected to be larger than it should be, because there is no friction in that force created. This is an important point to consider, that the force applied as couple inside the bracket is larger, so expected to have larger moment than it should be. With clear aligners, it has much better control, because clear aligner covers the tooth completely, unlike fixed appliance. The fixed appliance, to have good control, the maximum point that we can achieve by applying a force and allowing the wire to touch the tooth in 2 points, and this will give us a nice control. But with clear aligners, we expect the aligner totally covering the tooth. However, because of the transformation, the distortion that sometimes occurs with time, with the clear aligner, it's not good enough to rotate teeth. So for better control, the clear aligner companies, especially the Invisalign company, the Align company, created what we call attachments, and they used these attachments to create 2-point contact to have better mesodistal and buccolingual root movement. And this helped the appliance to be much more efficient in doing most of the orthodontic tooth movement. Like, for example, with clear aligner, because we have the attachment. I don't know if you guys are familiar with this, but if you go and read about it and find a picture with attachment, you can see that the having two attachments sometimes help to do bodily movement. And sometimes we add some indentation in the plastic itself, like we can add what we call power ridges on the on the labial side, that applies force on the crown in order to create torquing moment. So these kind of application help to improve or fine-tune the effect of the clear aligner. So just to summarize, how we control the tooth movement and minimize tipping effect by applying either force within the bracket. This is in case we want to move teeth lingually. Alright, so apply lingual root torque. And if we want to move the tooth, sliding it, like in case of extracting premolar and sliding the canine back, moving it distally, we can apply torque or we can apply 2-point contact by using twin bracket that has 2 wings. So every time the tooth tends to tip, it will be resisted by having 2-point contact in the bracket that help to upright the tooth. So the force generated will depend mainly on the dimensions of the wire and on the bracket width, dimension of the brackets. So for example, if you use a very small dimension wire like 16 in 0-2 bracket size, then you expect to have a lot of tipping, because you will have a lot of play inside the bracket. Again, if we have a narrower bracket, we expect the movement to be different than if we use wider brackets. And let's see how this size of the bracket can affect the type of tooth movement. Wider brackets will apply more bodily movement and minimize moments more than the narrower brackets. Why? If we look at the example we mentioned before, that if we have a tooth that we want to move distally, like the canine, moving it distally, when we extract first premolar. Then, of course, the bracket will be like 10 millimeter away from center of resistance. So the retraction force required is around, applied is 100 grams. So we expect 100 gram force at 10 millimeter distance from the bracket, or from 10 millimeter distance from the center of resistance, will create 1000 gram millimeter. So to overcome this, we need counteracting moment of 1000 gram millimeter. With narrow brackets, which is 1 millimeter wide, in order for you to create a moment, you have to use a force of 1000 gram, because as I said, the moment of the couple can be calculated by measuring one of the forces times the distance between them. So if the distance between the two edges of the bracket only 1 millimeter, so the total force needed 1000 gram, which is very difficult to apply. You need a large force. But with our regular brackets, which is 4 millimeter wide brackets, you can generate 1000 gram millimeter counteracting or counterbalancing moment by applying only 250 gram of force, because 250 gram of force times 4 millimeter will be equal to 1000 gram millimeter. That will be enough to counteract the moment of the force. Not only that, when we use wider brackets will have or minimize what we call the binding effect. Binding effect is one of the resistance to sliding methods that we encounter when we try to move the teeth. So the minute the wire develop an angle, or the tooth bends over the wire, this will create resistance to sliding called binding. So having narrower brackets will create more binding, which in turn will create more resistance to sliding than wider brackets. This is another advantage for wider brackets. However, having too much wide brackets is a problem. Why? Because to the very wide brackets, if we have wide brackets here and here, this will reduce the intercanine distance, which make the wire stiffer, because as I said, when we increase the wire between the intercanine, between the two brackets, I said intercanine, sorry, when I say interbracket distance, if we increase the wire between the two brackets, this will create or add more flexibility to the wire. And having wider brackets on each side will create shorter intercanine distance and shorter wire between them, which will make the wire stiffer. So using extremely wide bracket is contraindicated in orthodontics. That's why it's advisable to have like half tooth width. Like a bracket should be half the tooth width. And usually this is the situation for most of the bracket that we use nowadays. The original slot size that was used by Angle was 022 by 028 of the inch, which is 22 by 28 mil. And why was that? Because at that time he was using gold wires, and most of the time his brackets were narrow brackets. Why? Also because at his time he didn't used to do extraction, so there was no sliding. So his main use of rectangular wire is to apply torque movement. So with gold, it was suitable to apply efficient torque at that time. Stainless steel wire The use of 0 to 2 wire was very stiff because it was different than gold, and having adequate stiffness was in the range of 18 mil. So that's why people felt that they wanted to reduce the size from 22 to 18 mil bracket. That's why we have now two sizes of brackets. We have 22 by 28 slot size, and we have 18 by 25 slot size. So you can see now some of the instructors will ask you to do 18 brackets, and some will ask you to do 0 to 2 brackets. What's the difference? There's no big difference between them except for some variations. Like for example, if you look at when we do, of course, in orthodontic we do a lot of sliding. So in order for you to do sliding in 0 to 2 or in 18 brackets, you have to have minimum of 2 mil clearance between the wire and the bracket to minimize friction. So usually when we do 18 slot size, 18 by 25 brackets, you expect when you slide to use 16 round wire. But you cannot use 18 mil round wire, because the 18 wire will create a lot of friction in 18 brackets. On the other hand, if you want to use 0 to 2 wire, you can use 18 mil 0 to 2 bracket, sorry. You can use 18 mil wire because you'll have enough clearance that will prevent or minimize friction. Using 16 mil wire, however, during sliding might create tipping for the canine. When you do canine retraction, might create tipping for the canine because it's not stiff enough. But with 18 we cannot use any larger dimension wire. But with 0 to 2 we can use 18 mil, which will resist tipping effect more than the 16. So maybe when we do a lot of sliding mechanics, it's much better to use 0 to 2 bracket size than 18 ml wire. However, when we want to do torquing effect using very large size wire like 0 to 1, which is closer, the closest one to 0 to 2 bracket size, is problematic because it will have a lot of stiffness in the wire. So you'll have less springiness and range in torsion. So this is one of the disadvantages of the 0 to 2 brackets. So nowadays, it's more preferable if you want to do torquing and you want to do finishing. It's better that we use night eye. The A night eye wire in a larger dimension will help to create, to control torque as claimed or proposed by the author, and also the beta titanium. Beta titanium, which is the TMA wire, is the best wire for finishing because you can apply a lot of a torquing effect, and you can fit the wire easily in the final stages of you can fit a large dimension wire easily in the final stages of finishing. Second part of chapter 9, and as you can see, my explanation here is comprehensive. I'm trying to explain the whole text sentence by sentence in most of the slides, and the reason was that this is made for junior students who read the book for the first time, and also because it's really a comprehensive book with a lot of information in it, and it's sometimes that it needs that we understand certain ideas before we understand what's in the book. And thank you again. I hope you like it.